Today we study ESA7H matrix representation of a scalar product. Because we have already studied the matrix representation of scalar product in the main theme, today we focus on the direct product that is closely related to express the completeness relation. Projection operator. First, we consider a vector whose Cartesian components are A1, A2, and A3. The matrix representation of this vector is a column vector. Sure, you can also employ row vector representation, but we have chosen to employ the column vector representation. This one can be expressed as a linear combination of three basis vectors and these three column vectors represent the unit basis vector of the Cartesian coordinates. While we define the product of one row and one column matrix that is actually a vector, as the product, and third one, plus. This one is identical to the scalar product of A and B if we express them in terms of the Cartesian unit basis vectors. Now we exchange the column and row. We have a column vector and row vector, and there is a cross. This sign, this symbol, indicates it's a direct product. The direct product is a matrix that can be generated by two vectors. Here, a column vector with the three elements x, y, and z has a factor in the 9 elements, x in the first rows, y in the second rows. So these three rows will be x, 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 y, 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 z, z, z factor. And then we have a row vector on the right side that determines the first column has the factor a. The second column has a factor of b, b, b. And the third column has a c, c, c. This way of defining a direct product can be extended to an arbitrary number of dimensions. But let us focus on the 3x3 case. First, we separate the x component vector out of a vector. X component vector is a Cartesian component. We have E1 and A1. A1 can be expressed as a scalar product of unit basis vector along the x-axis and the original vector. Therefore, if I substitute this one in here, then we have this expression. All right. And then E1 hat can be expressed as a matrix representation 1, 0, 0, and this is the coefficient. In a similar manner, we can express the second component, the y component vector and z component vector as well. Now, let us consider the direct product of a unit basis vector in a column and it's a transpose, that is a row vector. The column vector matrix representation of this E1 hat, it is 1, 0, 0, and matrix representation for the transpose of this is a row vector 1, 0, 0. We can construct the direct product out of these two unit vectors. The result is first row has the factor of 1 and first column has a factor of 1. Other than that, any other element has a factor of 0. At least a single 0 will give result in the vanishing element. As a result, the only non-vanishing element in the outer product, or this direct product of these two identical unit basis vector, is this. Other than that, everything else vanishes completely. We say this one single non-zero element in the 1, 1 element of this 3 by 3 matrix is pi 1, that is called the projection operator. Projection operator along the x-axis. In a similar manner, we can construct the projection operator for the y component. Projection operator pi 2 can be constructed by multiplying E2 hat and its a transpose row vector as a direct product. In this case, second row and second column may have a factor of 1. Other than that, everything else has a factor of 0. As a result, the only non-zero element is the 2, 2 element. Exactly the same way is applied to find out the projection operator for the z-axis that has a non-vanishing element in the 3, 3 element, except that everything else is 0. We recall that we call the completeness relation, that is, any vector in the three-dimensional Euclidean space is a linear combination of a 3-unit Cartesian basis vector. And Cartesian components A1, A2, and A3 can be extracted by multiplying E1 hat, E2 hat, and E3 hat to a vector A. This one is project out the scalar vector that is called the Cartesian component along x, y, and z axis, and then multiply the unit basis vector corresponding to that axis. This is called the completeness relation. And actually, what we want to do is apply some operator that does not remove any single element in a three-dimensional vector, is multiplying the unit identity matrix that does not transform this matrix at all. By the way, we recall that this pi 1 is this. That is pi 1. And this is pi 2 and pi 3. If I sum these three projection operators, projection matrix representation for the projection operators, we obtain the identity matrix, the matrix element for the identity operator. As a result, if I sum these all, the final result is nothing but the identity. It does not change at all. And the effect is, we recall that E1 transpose and A as a column vector. This one, something like that. What's that? This E1 transpose is 1, 0, 0, and A vector is A1, A2, A3. The final result is A1, and because they are both of them are 0, A2 and A3 contribution does not contribute to this product. As a result, this is to collect the Cartesian component. Once this operator is multiplied to the column vector representing the A vector, it collects A1 only, and it is to be multiplied to a unit basis vector. As a result, this sum of the three projection operator along the Cartesian coordinate is nothing but identity. And finally, this first contribution is A1, 0, 0, second contribution 0, A2, 0, and third one is a 0, 0, A3. If I sum them all, I can reproduce the original vector, the matrix representation for the original vector A. So this is the reason why we say that this is a completeness relation. We reproduce A vector in the Euclidean space if I multiply all possible projection operators along the Cartesian coordinates. We employed matrix representation in the two-dimensional Cartesian coordinate system, E1, E2. Okay, and then we have a prime basis vectors that can be obtained by rotating E1 and E2. So E1 is here, E2 is here, and then we rotate them by an angle of theta to have E1 prime and E2 prime. And this is angle theta. Using this relation, we can find what the scalar product between two unprimed basis vector and prime basis vector by considering the angle between any two of them. We remember any vector can be expressed as a linear combination of E1 and E2, and the completeness relation in this in terms of E1 and E2 vector, E1 prime can always be expressed completely in this form. So this way of writing the completeness relation can be employed to find out, generalize this one to both the E1 prime and E2 prime. Both of them can be expressed in terms of E1 and E2, and we apply the angle, we make use of the angle between any two unprimed and primed unit basis vector to express them, these directional cosines, in terms of sine or cosine with appropriate sign. As a result, the matrix representation of E1 prime and E2 prime in the basis of original basis vector is, for example, E1, E2, and this is E1 prime, this is cosine, this is theta. E1 prime can be expressed as a cosine multiplied by cosine theta E1 and sine theta E2. This is a half a pi minus theta. That's the reason why the matrix representation in the original basis E1 and E2 to express E1 prime is this. And in a similar manner, E2 prime can also be expressed, E2 prime can be expressed into the cosine with E2, and this angle is this angle, half a pi plus the theta, so it has a negative of sine of E1. Okay, that's it for today. Thank you.